I'm Isobel, as mentioned. Really excited to be here and to talk to you all about class fixes, or how you can become the Rust compiler yourself. So, quick mini agenda, basically just intro. Then I'm going to talk about class breaks and how we can invert that concept and use it to think about things in terms of class fixes, and then how that can help you to become the compiler, either when you are writing Rust or also when you are not writing Rust. And then maybe a quick Q&A at the end. You can definitely come find me afterwards. I'll stick around and I'll be here all day and so on. More than happy to talk about this. So who am I? I work on open source, mostly open telemetry at Lightstep these days. I used to work at on Cloud Foundry at Pivotal. So I mostly do Go by day, also some Python, Ruby, JavaScript, done a bunch of whatever is kind of necessary. A lot of Bash, turns out, often is what's necessary. But by night, Rust is where I'm happiest. Also get to maybe do a bit at work and hopefully more soon. But mostly Go these days at work, or text, because specs. So what are the goals of this talk? What do I hope that you can take away from it? Basically, the hope is that you'll be able to use this as a framework for approaching error mitigation. So in other words, how to not necessarily solve individual bugs, but instead how to prevent whole categories of bugs. And ideally, oops, sorry, I thought I had another slide in there, but forgot to put it into this version. Ideally, how to actually use Rust and therefore leverage the compiler directly, but also how, when you're not using Rust, how to essentially think the same way that the compiler is, and therefore kind of conventionalize some of the things that Rust does for you. So, class breaks. Start there. Basically, this is a security term. Don't think it was originally coined by Bruce Schneier, but he's certainly how I first heard about it. So, a class break is a particular security vulnerability that breaks not just one system, but an entire class of systems. He has a really good essay about this out there. So an example would be locks. You know, traditional locks, you have one lock, you need one key for that lock. Therefore, in order to break into, let's say, 10 houses, you would need to break into 10 locks separately. So that's essentially safe in that regard. However, there are your locks. However, if you instead have the same lock, for example, maybe you have a skeleton key, or the TSA, they had this issue a few years ago where they had a skeleton key for all luggage locks, and someone printed, like the Washington Post, I think, printed a copy of it online, basically. So now suddenly everyone had access to every luggage piece out there. Or similarly, smart locks also have the same potential vulnerability, and was exploited a couple years or so ago with a hotel where basically someone went and held all the hotel guests hostage. I think this was in Austria. So essentially, there are some niceties that you get from having, from essentially drying up your locks, drying in the software sense, not in the meteorological sense. However, there are also potential problems. And this isn't just true for things like locks, it's true for basically every piece of, every dependency we have. Then every machine using that same version of OS, or another version affected by the same vulnerability, is affected. Those are thermometers, for anyone who can't tell. Turns out it's really hard to draw thermometers. I am not an artist. So essentially, hopefully you're using a common operating system. I mean, we're at RustConf. I suspect that some of you here today are also working on your own, and that you have very awesome reasons to do so. But in general, if you are running most companies, you probably don't want to be writing your own OS from scratch for this, just in order to skirt around class breaks. If you're, Google or whomever, you might have your own fork, or you might go and write Fuchsia or something. I suspect that there are some Fuchsia people here, especially since I think it's largely Rust. But in general, if you are, for example, someone like me working at like 100 or so person startup that is not focused on delivering an OS, that probably isn't something you should be focusing on, because you will instead have other problems if you try to write your own. So essentially, class break once, break everywhere. So what if we invert that? What if we instead have something that we fix once and thereby fix everywhere? You can think of this as a class fix. That's what I'm calling it. So what would it mean to fix our code everywhere? If we think about bugs, and if we think about them kind of in just like a basic CS 101 sense, at least, then you essentially have kind of three main categories of bugs. You have logic errors, so things where you as the programmer got something wrong. So maybe you, for example, the other day, a couple of coworkers were working on an interesting algorithm, and they were misimplementing it. The algorithm was theoretically correct, just the implementation was wrong. Then you have runtime errors, which most of us have probably encountered, hopefully not too much in production, but almost definitely in production. And because these happen most often in production, they're quite hard to tackle. Then you have compile time errors. And while these might be annoying when you're actually writing code, they're also kind of awesome in another sense, in that if you know at compile time that something doesn't work, then you can just kind of fix it before you deploy it, or send it out to your customers or whatever, depending on your particular deployment your delivery mechanism. So compile time errors essentially are the safest of these three categories. In that regard, they're kind of better than the other two types of errors, in that as an engineer, it's a lot easier to fix them. So the more that we can move logic and runtime errors towards becoming compile time errors, the safer our systems are going to be. Essentially, if we can downgrade a bug's category, ideally all the way to compile time, then it's, I would argue, a form of fixing it everywhere. So the Rust compiler does this a lot for us. And sorry for the large wall of text up there. Basically, Gary Bernhardt, he of Watt fame, also The Future of JavaScript, or Life and Death of JavaScript, I think it's called, had this quote the other day: "Programming is rolling boulders uphill forever. A type system tells you when boulders roll back down. If you look at that and say, I will not expend effort to know when boulders roll back down, you should at least know how much effort you're talking about versus how many boulders it stops." So he was talking mostly about type systems in this context. I think it was a tweet thread about TypeScript versus regular untyped JavaScript. However, you can also extrapolate and apply it to other aspects of a language, even just kind of from the ground up. You can think of how basically any modern language that we're using improves a lot on like assembly, for example. Again, some of us are probably using assembly. I personally am not, or haven't since had to for CS reasons, but day to day, I suspect some people are, which is awesome. So, Rust. That is supposed to be a cape. It's okay if you think of it as a chef's hat instead. I won't blame you. But the point is, Ferris is awesome. So, Rust type system. gives us so many niceties. It's awesome. I'm not going to go into all of them here because I think most of us are probably pretty familiar with them, and a lot of them also aren't. The improvements that Rust type system gives us compared to most other languages type systems are awesome, but in some ways less relevant than other things. Also, more languages are kind of moving towards Rust-like type systems, I would say. So, for example, TypeScript has pattern matching similar to Rust. I don't know exactly how similar. I haven't really written much TypeScript, but it has some. Go is getting generics. It's still a bit unclear what their generics are going to look like, but they'll have generics. I really like Rust type system, but the general factor of kind of a type system versus no type system. I think most of us are familiar with how having your compiler be aware of your types and thus stop you from trying to like add an int to a string, for example. It's pretty nice. When we write untyped languages, we can do that to some extent. We can, anticipate that we probably shouldn't be adding an int to a string. However, it just is nice to have the compiler do that for us, which gets back to what Gary Bernhardt said here about how much effort you're talking about versus how many boulders it stops. Like, you as a programmer can stop some by just kind of thinking, knowing that like you shouldn't add an int to a string. However, when your compiler does it, you get more or less 100%. Again, depends on whether you have like any types or things like that, but it moves you towards perfection. So, another big thing, Rust doesn't have reflection. Which in some ways might make it harder than other languages. Getting back to the analogy of how many boulders it stops versus how much effort it takes to harness it in order to stop those boulders. However, what it gives us instead is pattern matching. I know that that it's not a perfect flip. However, in many ways, it gets you what you might what you would use reflection for traditionally. So essentially, if you wrap tricky enum types with their own types, you can capture a lot of the use cases for reflection in the first place. An example, here's some Go. It's very messy Go, but basically there you have, you want to open a database connection. It varies depending on what database type you're using. So you have this OpenDB function that just takes a DB type, which is supposed to be its own type, but this code compiles despite the fact that it lets you throw in random strings. So here we have two defined DB types, Postgres and MySQL. We're using MySQL correctly. However, Postgres, there's a mismatch between the strings, and then this switch statement also lets us handle foo, which is not a database. And it lets us call the function with something that, again, is invalid. Literally the string invalid in this case. So while we have the type there to kind of hint at ourselves and other engineers, I personally like to think of kind of myself from yesterday as another engineer because I have really bad short-term memory apparently. So it lets you suggest that you should be using a database type, but it isn't really that good at enforcing that. And a lot of other languages that have enums have kind of similar shortcomings in their types. Go also does have enums, but they're about as unsafe, I would say, as doing a type like this. Not unsafe in the Rust sense, just unsafe in the sense of like the compiler doesn't really let you do anything interesting with them. If you compare this though to what you would write in Rust, here you just have a simple enum, and then you have an open method which is aware of what type it should be handling, and the Rust compiler is able to tell us whether if we are missing a type or not handling something. it also is able to ensure that we are handling everything that we should be, and that we're not handling anything that is invalid. So now we can just say Postgres open and carry on. If we went back to Go, we could kind of hack something similar-ish together. This is not the neatest Go code, sorry, but basically, for those unfamiliar with Go, capitalized things are public, uncapitalized things are private. So here, this DB type interface is something that can only be implemented within the package because it has this private method that it requires is DB type. So now we have two types that implement the interface, Postgres and MySQL, and they both are forms of this DB type, which again we can use anywhere. But we can only implement within the one package. And then they also have their own open methods. And so now you can just say postgres.open. Kind of similar to what you would do in Rust. It just doesn't have quite as much of what the compiler gives us. And in my opinion, at least, this is a lot messier than what you have in Rust. Certainly, Rust, fewer lines of code. And if you were missing a type, the Rust compiler would complain, unless you were handling it in some other way. But again, the compiler would ensure that. Another thing, option instead of null. So who here has ever encountered some sort of null pointer exception? Yeah, I think that's everyone. So option, pretty awesome. Some languages, like Java, for example, are moving in the direction of gaining it. Personally, the last time that I wrote a application in Java, we attempted to use option. However, half the team wasn't really on board with it, so we still kind of, and then we were using a bunch of libraries that didn't support it, and we ended up having nil checks all over the place despite having option. I imagine that others have more success with it, also that another group have even less success than my team did. So if we, again, go back to Go, here we have this kind of plain bit of a canned example here, where we have an interface and then another interface that contains that first one. So interface and interface container, really creatively named, I know. And in the container one, we call into the first one's method. So we say, we have this wrapper.internal.foo, essentially. However, as you see at the bottom, basically, when we use a valid interface for this, things work properly because our struct implements foo correctly. However, in Go and in many other languages, nil is a valid empty nil satisfies any interface, and so nil in this case is actually of type interface. It just doesn't actually implement foo, and therefore when we attempt to call foo on nil, it compiles, but we get a panic. So essentially, there are two main mechanisms that we can use in languages that don't support option. So one is on get, and that is to return basically a bool. This is assuming that your language has like tuple types or multi-return values. Otherwise, you're kind of stuck with the second option. And then the second option is to use the null object pattern, which basically is, well, I'll show you in a second. And so these partly are dependent on what language you're using, since, again, not all languages support like tuples or multi-return values. Also partly dependent on how you want your client to consume it. So if we look at examples of both, here this one is using the first one where it implements it on get by representing whether or not it existed with a bool. So essentially in here, we check on the getter if the thing is nil, and if it is, we return basically a nil value as well as false. And then when we actually use it, we say, I didn't highlight that. We say, if the thing actually exists, then use it, otherwise just carry on. And so in this case, the program will print hello RustConf and then just nothing else. It doesn't even print like an empty line or something. It just doesn't hit that line. In more realistic scenarios, sometimes knowing that the thing is that the thing wasn't ever set is useful. That's why in Rust we often like having option rather than using the null object pattern. And then the other option is this null object pattern, where now we have a no-op struct. And on the setter, or in this case in the constructor, we check to see if the thing would be nil, and in that case, basically backfill it in with a no-op thing. So no-op in the sense that like it'll comply with all the interfaces and so on without blowing up, but it doesn't do anything interesting. So in this case, for example, it prints an empty line on, or it returns an empty string on foo. Go doesn't support like nil for strings, so empty string is all you get. And so in some ways, using this one is nicer since it's shorter. On the other hand, you don't know how to distinguish between empty string and unset. So it really just depends on your use case as well, again, as your language. And essentially there again is where the no-op gets provided. Then the borrow checker. So I know that there's a heart here, and we all have probably struggled with the borrow checker at some point, but you know, it's kind of our frenemy. It's there to help us at the end of the day, and even if it means that sometimes writing the code is trickier, it means that running it is a lot easier. So here, again, don't mean to be picking on Go, it just was convenient since it's a language I personally write a fair amount and it also is typed. Here's a little program where basically half of the time it attempts to append something to an array in a what's called a Go routine. So basically in a, not a thread, but like a green thread type thing. However, Go's slices or arrays are not thread safe, and so this part will give you some funkiness. Now, the Go compiler has a runtime race detector, but it's only runtime. So here, like if you build the program with the race detector on, it thinks that everything is hunky-dory. We got a nice exit 0. It thought that the program was great. When we actually attempt to run it with the race detector, half the time we get this, where it finds the data race. The other time, we don't have any complaints. We just have our nice little empty array. Also, in here, there's kind of an extra data race where, since it doesn't actually wait for the Go routine to complete, even when it does detect the data race, it also doesn't successfully append it in time. Essentially, the main doesn't wait for that Go routine to complete. Now, compare this to Rust, where the naive version would be you have, again, a vec of ints, and you attempt to push that, something in there, into there in a thread. And I know that that's maybe not the prettiest way of checking to see if the time is even, but it was a way. Could have also probably just thrown in a rand too or something, but anyway. This doesn't compile. We get a nice set of errors, things we've all probably seen before, basically, where the compiler helpfully tells us, hey, there's a problem. Here's where it is, and here's how you might be able to fix it. And so, essentially, if you only use type-safe threads or methods, things become happier. So now, back to Rust, if we use an arc and mutex, I just was trying to omit the import statements so that things could be bigger font in here. Then now this program compiles and is safe. There's no longer a data race. Goes, sorry if that's hard to read at the back. Basically, I made a thread-safe int slice. Again, they don't have generics right now, so bear with me. But basically in here, whenever you're attempting to append, it grabs a lock. And when you are attempting to read from it, or just grab the string in this case, the stringified version, it again sets a read lock. And now this is safe. It's grosser, but it's safe. So here we can see that with the race detector on, we were able to successfully print both the empty and non-empty versions. So in short, thinking of things in terms of class fixes can really help you when you are actually writing Rust because the compiler does it for you. But even when you're writing other things, other languages, you can still basically treat some of the Rust compiler niceties as conventions and attempt to kind of backfill your own patterns for runtime. And then you can go to your team and say, hey, we're using all these patterns. They're better than having runtime errors, but they're still conventions. What if we had the compiler do it for us? And then your team can become that much more powerful. Thank you.